Welcome to the New Quantum Era. I'm your host, Sebastian Hassinger. One of the things I keep coming back to on the show is a deceptively simple question. What can quantum computers actually do that classical computers can't? We've explored it from the hardware side with Rob Scholkoff on dual-rail qubits, with Jens Eisert on benchmarking, with Hrant Karibian on peak circuits, and we've looked at it from the complexity theory side with Scott Aronson and Dorit Aronov. But the specific question of whether quantum advantage has already been achieved, whether we've crossed that line, is one where I've found surprisingly little consensus, even among experts. My guest today, Dominik Hangleiter, set out to settle the question. Dominik is an Ambizione Fellow at ETH Zürich and a postdoctoral fellow at UC Berkeley's Simons Institute. He just published a paper just a week or two before we sat down called Has Quantum Advantage Been Achieved? It grew out of a series of blog posts he did on the Caltech Quantum Frontiers blog, which itself grew out of a moment at a conference when Dominik asked a room full of physicists whether they believed quantum advantage had been demonstrated. He expected near unanimity. Instead, the room was split. That surprised him enough to write tens of thousands of words about it. What I find compelling about Dominik's work is that he's not a cheerleader. He's published attacks that broke proposed verification schemes for quantum advantage. He's shown that certain noise regimes are classically simulatable. And yet his conclusion, after a decade of working at the intersection of complexity theory, quantum physics, and the philosophy of science, is that yes, quantum advantage on these random circuit sampling tasks has been achieved, to the same standard of evidence we'd accept for any physics experiment. Not beyond all doubt, but beyond reasonable doubt. But here's where it gets really interesting. Dominik isn't stopping at the claim. He's building the theoretical scaffolding for what comes next. Fault-tolerant, verifiable quantum advantage using error-correcting codes co-designed with specific hardware. His collaboration with the Harvard neutral atom team produced one of the most elegant proposals I've seen for how to get there. And along the way, he's grappling with some of the deepest questions in the field. Why is basic arithmetic hard for quantum computers? What makes interference the engine of quantum speedup? Can different hardware platforms contribute different native strengths to a heterogeneous quantum future? Dominik also has an unusual background. He studied philosophy and math alongside physics, and it shows in how he thinks about evidence, verification, and what it means to know something about a computation you can't classically check. Before we get into it, this episode is brought to you by Qubits OK, a dedicated job board and research digest for quantum computing. If you're building a career in quantum or hiring for one, this is the signal in the noise. Every week, they send curated job alerts filtered by over 400 specialized quantum tags, trapped ions, QEC, quantum ML, you name it. They also run a daily archive digest that surfaces papers that actually matter to your specific research interests. That daily digest is actually one of the ways that I find people like Dominik. It's free to subscribe. Head to qubitsok.com and sign up in 30 seconds. And if you're hiring in quantum, use the code NewQuantumEra-50 for 50% off your first job posting. That's qubitsok.com, code NewQuantumEra-50. And now, my conversation with Dominik Hangleiter. Hi, Dominik. Thanks for joining me.
Hi, Sebastian. Great to meet you.
I'm happy to have you on the podcast. And if you could, can you start just by sharing your origin story with us?
My origin story. I guess my origin.
Your quantum origin story.
My quantum origin story. Yes. Great. What is my quantum origin story? I studied like a bunch of different subjects, mostly physics, but then also some philosophy and math. And what really got me into quantum, I think, is this question of verification. Like this fundamental question: can you verify, a quantum computation, even though you have no way of simulating it on a classical computer? And I guess that's what sort of got me into the field initially. And then I got really excited about complexity theory and, all these topics, which I guess we're going to discuss in more detail today.
Yeah, absolutely. Absolutely. So you got your PhD from the Freie Universität, I think, right? Of
Exactly.
Berlin?
Yeah, in Berlin.
Right. Right. You got your PhD under Jens Einser, right? Yeah.
That's exactly right. Yes.
Yeah, I had him on the podcast. I actually interviewed him at the Simons Institute
Oh,
a couple of years ago.
Wonderful.
Yeah, so that was a great guy. I think he's a incredible energy and has 27 things going at once all the time. It seems like
so true. Yeah, I love Jens. He's great.
great collaborator. So the reason I wanted to have you on was a series of blog posts initially on the Caltech blog, Quantum blog, that you just posted to the archive a couple of weeks ago, or maybe even last week, around quantum advantage. And I remember the original blog post grabbed my attention because you started by saying you were giving a talk and you asked the audience, who here thinks there has been, conclusive proof that we've reached quantum advantage. And you were shocked at how few people were really convinced. Most people were on the fence or very skeptical. Why was that surprising to you?
Well, I've been working on quantum advantage for, I guess, more than 10 years now. And one of these big moments was the 2019 demonstration of quantum supremacy, as they called it. And since then, there's just been a lot of development in theory and more experiments. I remember at the time there was, this big fuss about, IBM put out a paper just a few days after being oh, we could simulate it on our huge, I guess, the biggest supercomputer.
Frontier, the largest supercomputer in the world. No.
Right. And
well,
then it took
not worth the effort, I think is the
yeah. I don't know what exactly the framing was, and then it did take a couple of years or so until I think there was to my eyes, pretty conclusive simulation of that experiment. But, the field progressed on and there was more theory development and more experiments which were bigger and hadn't been simulated. And so in my mind, when I gave those talks last year, I was surely everyone's going to be convinced of quantum advantage now. We've had 6 experiments and they've grown and they've gotten better and we have all this theory around it now. So I was really surprised when, to these very different audiences, there was not a consensus. It was very split between people who were skeptical or who thought there hadn't been a quantum advantage demonstration. And I think for very different reasons. And I guess the blog posts were meant to address those potential reasons.
Yeah. And just to rewind and set the context, so the 2019 experiment that Google carried out, this was a random circuit sampling experiment, right? Can you explain a little bit about how how that's designed, I guess?
Yeah, that's exactly right. So I guess starting in the early 2010s or so, people had been starting to think about, what would the first big milestone for the field be? And they came up with this idea of just running a really trivial experiment in some sense, which is just run a random quantum computation. And, those computations, they started coming up with these arguments that they would be really hard to simulate on a classical computer. And so this is random circuit sampling, which is, you have a small quantum computer and you run whatever computation is kind of native on that device, but in a random way. And you do it as far as you can go until the noise drowns you, basically, or before the noise drowns you, ideally. And then you get samples. And the task, which is kind of an unusual task when you think about computation, usually we think about it as, I want some number out of it. I don't know, the energy, ground state energy of a molecule, or I don't know, the factors of a large number. So the sampling task is kind of unusual, and that's maybe been kind of unsettling to people that it's such an unconventional, maybe computational task. Right, but it is what I guess distinguishes it from what I would call more physics experiments or analog simulation experiments or so is, sure, let me start differently. You could have also thought that just running some quantum system, letting a quantum system coherently evolve for some time, that's something that's hard to simulate on a classical computer. So you could be like, oh, well, this is quantum advantage. But really what sets random circuit sampling apart, even though it is still kind of a native computation on a quantum device, is that it's really programmable. So it's really, I sort of give an input to the device, right? I'm the user of the device. I design a circuit. I draw it randomly, yes, but then I give the circuit to the device, and then whoever controls the device runs the circuit and gives me back the samples. And I can, in principle, do the same thing on a classical computer, right? I can just simulate the circuit and create samples. And really the point is that one is much harder than the other.
Right. And I guess that would distinguish it from other advantage experiments that have been, as you say, either analog or they lack that sort of universal computation aspect to it. Is that right?
And right, exactly. And there is a continuum, like there are these maybe analog simulators where you can control some parameters. So it's like a very restricted model of computation, if you will. One of the first proposals for these random circuits was IQP circuit sampling and boson sampling, both of which are also not universal circuit classes. And yet they're like, in my eyes at least, much, much closer to this ideal of a universal programmable quantum computer than maybe these analog simulators where you just have a physical system that sort of has some native dynamics.
Right, that's parameterized. You can plug in your values, but you don't actually have control over the time evolution or whatever the dynamic is that it's carrying.
Yeah.
And so you mentioned there is plausible, a convincing simulation of the original Google experiment, but is that because they're limited by number of qubits or the connectivity or the coherence time? But if the Sycamore chip had been higher quality and less NISQY, that experiment could have been unsimulatable?
It's a little bit of everything, I would say. It's a little bit of, the number of qubits was maybe not that large, the circuit depth, so the, number of layers of elementary operations that you do wasn't that large, and the fidelity, so the quality of the computation wasn't that big. And so the simulation really used all of those properties in order to just about be able to simulate it, basically.
Right. Because I notice when you look at quantum computation simulation packages like Penny Lane or that sort of thing, they seem to trade off the sparse connectivity with the number of qubits they can simulate. You'll see claims of being able to simulate hundreds of qubits, but it's with very sparse connectivity, and that's sort of one of the bigger dials that you can adjust to make something tractable or non-tractable on a quantum context,
right.
I think, right?
Yeah, so really the simulation algorithms that people use are these tensor network algorithms. And there we really think of a computation as something in space-time. So you really think of a big block of elementary tensors and you stitch them together. And the simulatability is really a property of this space-time block, not so much of the individual parameters.
Yeah. And so it's random circuit sampling is an arbitrary task. It doesn't have sort of a pragmatic agenda or outcome to it. But it seems like from what you've written that you're making an argument that, back to your point about how do you verify something that is classically hard to do, that there is this method, XEB, that sort of emerged out of random circuit sampling. It's one of the tools that potentially we can use for verification beyond that simulation barrier. Is that right?
Yeah, maybe that's not how I would phrase it.
Okay.
So I wouldn't actually call random circuit sampling verifiable. Not verifiable in the sense that I guess I was alluding to originally, where we can really be convinced, sort of without any doubt, that this is what has been done. The problem that XEB solves in the context of random circuit sampling is really that the distributions, so the probability distributions that these samples come from, they're really, really flat. So they're in some sense quite close to uniform samples. In particular, when you get samples from this quantum device, you'll never see the same sample twice. So this makes it really hard to distinguish against, say, a uniformly random sample. And that's the problem that XEB solves. Basically, by taking the samples from the device and then correlating those with the ideal probabilities, like the probability that I should have seen that sample. And then you'll eventually see like a small bias towards larger probabilities. And that signal you can pick up with this benchmark. So that's the problem it solves. The problem it doesn't solve is that you can verify random circuit sampling more efficiently than you can simulate it, because to compute XEB, you still need to actually compute those probabilities, which is exactly the task we started out. We started out being a hard task.
Right. Yeah, I mean, I find that threshold really fascinating, and I'm sure in some of the same ways, though not at the same depth as you, because it feels like we're heading towards a horizon where we'll have these machines that are kind of the ultimate black boxes in a way, because every classical computation you could, with sufficient pens and papers and human hands, like replicate or verify that calculation in some sort of classical way. Beyond this threshold of quantum advantage, there isn't a direct way to verify the work, because it is by definition not simulatable. What are the ways that you think might provide means for verification past that horizon of no longer simulatable classically?
Right. So I guess there's a bunch of layers to that. So maybe I'll start from how do you actually, I argued in the piece that we have actually demonstrated quantum advantage. So I must have an argument that there is some sort of verification, right? So the argument there is really that while we can't actually compute XEB, what we typically do in physics experiments is a lot of, extrapolation, a lot of sort of circumstantial experiments that validate that the experiment you really care about, or the property you really care about, the experiment is actually what you want to probe. And that's the sense in which I think these random circuit sampling experiments have been verified. There's a lot of circumstantial evidence that these devices actually sample from states with reasonably high fidelity, using maybe proxies for the XEB, using some theory about how the fidelity behaves as a function of what the noise properties are of the device. There's also different ways where you maybe run the circuit and then you invert it and then you hope to see the sample that you started out from, essentially. And all of those together sort of build the foundation on which I would argue that these random circuit sampling experiments have been validated to the same extent that any physics experiment, and I make the comparison to the Higgs boson, or gravitational waves are validated. So that's maybe the bottom layer at this threshold, I would say. And then beyond that, we do now have some schemes that are based on classically delegating a computation to a quantum device under the assumption that the quantum computer can't do certain computations. So it's sort of using the limitation of quantum computers in order to force them to actually do what you want them to do. So those are called maybe cryptographic proofs of quantumness if you just care about quantum advantage, but then you can leverage those to full-on sort of quantum verification. That's maybe one thing you can do. Another thing you can do is you can think of yourself as the verifier, say, as someone who has maybe a small quantum computer. Maybe I can produce single photons in a certain quantum state, and I can send those to the quantum device. Maybe big quantum computer who can do entangling operations, all the things we like. And then based on that, I can also do verification. So there's a bunch of different ideas out there, which leverage, in maybe the broadest sense, some limitations of quantum computations.
Interesting. Okay, so two things that I wanted to ask about. One, you mentioned inverting the probabilities. Would peaked circuits be sort of in that category where you're sort of embedding a signal in the inputs and seeing if you're picking that up in the outputs of in the distribution?
Yes. Yeah. So that's a good point. So peaked circuits, maybe I step back a moment and say what peaked circuits are. So peaked circuits is the idea that that you design families of quantum computations which are more like traditional computations in the sense that a certain outcome is the outcome you expect, right? And I said before that these random circuit sampling experiments are not like this at all. So peak circuits kind of want to interpolate between this ideal of a computation where you just get the outcome you want, the factors of a number, and these like almost completely random samples. By exactly as you say, like designing circuit families in a way that hopefully there will be a peak that you know when you know where it is when you design the
You're
family.
Anticipating it, yeah.
Exactly. So that's the idea, but you would still hope that, these sort of arguments for hardness from random circuits will carry over to this regime. Maybe even though now the distribution is much more structured. But it's unlike this inversion idea because an ideal inverted circuit is very trivial to simulate, right? I just, I know exactly what I should get.
Right.
So
throw a negative sign in front of it.
Yeah, exactly. In that sense, it's very much unlike it. So those are really more a proxy to estimate the quality of your gates.
Okay. And then you mentioned cryptographic proofs.
Yes.
Is that in the sense that you said using things that are difficult for the quantum computer to do? So what would be difficult for the quantum computer? Because we typically think of cryptography in the quantum sense of them magically having the ability to factor very large numbers through primes.
Right.
What's something cryptographically that's difficult for a quantum computer to do?
Yeah. So exactly. So as you correctly say, like one of the applications, I guess, of quantum computation is to break crypto.
Or threats.
Yeah, you're right. Yeah, I mean, I don't think it's a very good application, but here we are. Right, but that's really a property, at least to the extent that we know it so far, of the crypto systems that we use at the moment, which is mostly this based on integer factorization, RSA crypto system. But I guess since the advent of quantum computation, and probably even before that, people have been thinking more about crypto systems that would not be breakable by a quantum computer, or like alternative crypto systems that maybe would be breakable by a quantum computer. So just sort of to explore this world of what kind of crypto systems are breakable, what kind of crypto systems aren't breakable, what are the limitations. And one of the, I would say, most prominent crypto systems that I think there's pretty much a consensus that quantum computers would not be able to break them, but people, they're still quite a little bit unsure, I would say, is this problem called learning with errors, which is basically the problem of decoding under noise. So you have some, linear classical code, and then you sort of add errors to a code word. So, a code word is, some element of a subspace, a binary subspace. And then you add errors to it in a sort of sparse way. And the decoding problem is to, like, once I give you the erroneous code word, to go back to the original code word. And that problem turns out to be really hard.
Interesting. Is that because of no cloning and other characteristics of quantum states that make it difficult to revert to reconstruct or to make copies, I guess?
Yeah, why is that? I don't think it's related to no cloning. I mean, I don't think I can give you like a deep reason for why that is right now. I guess it's just not the kind of structured problem that maybe factoring is. Like factoring is really nice for quantum computers because you can like do a Fourier transform, and then it turns out after some like classical analysis of the factoring problem, there's a really nice structure to the factoring problem, which the quantum algorithm can make use of. And in contrast, these errors, that they kind of break all these nice primitives we have for quantum computers, like the Fourier transform.
Right. And I mean, there's a theme that runs through your work, which is I mean, you made mention sort of like the native abilities of quantum computers versus the native abilities of classical computers.
Yeah.
And it seems to me like there's a lot of value in probing exactly these strengths and weaknesses not only from a verification perspective, but where, I mean, the search for additional algorithms that will be, provide some massive advantage on quantum computers has been very, very difficult. And maybe in part it's because we don't understand those fundamental native building blocks of quantum capabilities. Is that sort of
That's
in part of
absolutely
your?
right. Yeah.
Okay.
Yeah. Like that's exactly the kind of the deep question I'm really
Right.
excited about.
Yeah.
Really understanding at a deep level what it is about quantum computers that makes them more powerful. What the types of operations are, maybe beyond some of the hand wavy arguments that people give. Let's say.
Yes.
Yeah. Yeah.
That's really interesting. And do you? I mean, in my mind, there's sort of two categories. And when I think of native capabilities, I think of Feynman's original sort of pronouncement in 1981. Nature is quantum. If you want to simulate nature, you're going to need a quantum computer. And obviously, there's quantum simulators, which are non-universal. But once you get universal programmability, you have enormous power in simulating. Choosing what to simulate, how to simulate it. But then there's this whole category, which Shores is sort of the most notable example of, which is what I would call like horizontal or applications outside of the simulations of nature, which have some other kind of commercial value or value creation possibilities in other industries that are not just about simulating a material or simulating a drug or those types of things. Is that sort of how you map those kinds of categories as well?
Yeah, pretty much. I mean, let me try and think of a good way to answer this question. So certainly, this like idea of simulating quantum systems using a quantum computer is very natural, right? Like, obviously, I mean, in hindsight, I guess, if I have the same type of system somehow, then it'll be much easier to simulate other systems of the same type. And so really the interesting applications to me lie in these, like more like cryptographic or sort of beyond simulating quantum systems applications, and seeing what kind of, elementary tasks are there that quantum computers are better at, and why is it that they're better at them? And maybe one of the answers you could give is, or that's often given, is this idea that quantum computers have this capability to do destructive interference. So I guess that's like a mechanism behind, say, the quantum Fourier transform or like Grover's algorithm, where sort of slowly you like dampen out. I like to think of it as computational paths, right? Like often we think of like quantum computations as sort of running in parallel. But really that's not the whole story, right? Really you need to like actually make sure that in the end only the things that matter end up in the outcome. And so you need a way to actually dampen out the things that don't matter. And in some sense, this interference is maybe an answer to that, but exactly for which problems we can use this interference, because it's very, very structured interference somehow. Like the laws of quantum mechanics are not arbitrary. I can't just, like tell the quantum computer to give me the outcome I want. There's rules to it. And how those rules apply to, say, computational problems that we face in maybe the real world beyond quantum simulation, which I guess scientists are really interested in, is I think a really intriguing challenge. Maybe also how it like interfaces with what classical computations are good at. So one thing I'm really excited about is to think about just basic arithmetic, right? Like classical computers are really good at doing basic arithmetic, but quantum computers, like it's really hard to do basic arithmetic. And so that's some
because of the sampling, the probabilistic sampling of the outputs.
No, not really. So this is for a different reason. I would say this is really for the reason that to do quantum computations we need this thing called fault tolerance, and quantum fault tolerance is very restrictive in terms of the operations that you can do on encoded information. And arithmetic is sort of one of the things that turns out to be really hard. at least in the ways that we
Oops.
know how to do fault tolerance. Yeah, and so
Right.
this is really a bottleneck for, say, running Shor's algorithm now, like actually doing this arithmetic and like compressing these circuits down and like understanding why it is that, for this task that maybe classical computers are really good at, like it's really simple for them to do arithmetic, quantum computers struggle somehow. And then there are other tasks where quantum computers are really good at, but classical computers struggle.
And that's sort of the segue I got, or the pathway where your work is turning into that fault tolerant compilation kind of research as
absolutely.
well, right?
Exactly. Yeah. So this is something that I guess I've worked on more recently. Is taking these ideas of what are the native computations, say these random circuits, for sort of like plain quantum devices where everything is noisy, and like merging them with like these early fault tolerance capabilities that we have now, and seeing, so what are the native operations now, and how, like, what can I really easily do on those devices?
Right. Right. And I mean, in those early models of fault tolerance, or maybe in any foreseeable model of fault tolerance, there's a round tripping between the quantum and the classical, right? There needs to be sort of mid-circuit measurement of some form, and then a feed forward that detects the syndromes and corrects the error syndromes in the forward-looking work. Is that potentially where the interplay of the strengths and weaknesses of quantum and classical can be, sort of applied?
I wouldn't say so yet, because that's really just like a layer below the algorithmic side. Like this is really at the layer of how do I correct for errors in the quantum computer. However, there are a lot of ideas out there now for how to interface quantum with classical computers, how to, maybe use a quantum computer to get like a good starting point for a classical algorithm or so. And those are really, I think, the ideas that we need to understand, like how quantum computers can interface in classical computations and really play out their strengths.
Right. Okay. So then to rewind to where I got it wrong. So then what you're talking about is compilation of a circuit in a fault tolerant regime that takes advantage of the native capabilities and avoids the weak points or the blind spots in that
exactly,
set of capabilities. Okay.
That's exactly right. Yes.
Okay. Yeah, I find it really fascinating that not only is fault tolerance giving rise to already very divergent definitions of what a logical qubit is, but also those definitions of logical qubits, which differ from modality to modality and vendor to vendor and variation of modality to variation of modality. But it also has huge implications for what the abstraction looks like for how to program logical qubits and compile circuits for fault tolerance. So, I mean, it seems like you've got your work cut out for you.
Definitely. Yeah, definitely. I think there's a lot to be done in the next few years on these different levels of the, I don't know if you want to call it hardware stack or so.
Yeah. And do you, I mean, you're operating at this in the realm of theory. Do you have a sense for the implementation of the theoretical stuff the theoretical fault tolerance compilation, let's say, that's going to, the implementation of that is going to be very different from one type of qubit to another, one vendor to another. Have you tackled that sort of the implementation side of it?
Yeah, totally. I guess I'm just not used to the vendor lingo.
Yeah. But I'm a technologist, not a physicist.
Right. Yeah. That's right. No, exactly. And I think that's what's so exciting about it is that, maybe some hardware platforms have different native capabilities than other hardware platforms. And okay, not maybe, they do, right? The question is, do we leverage, is there ways to leverage those native capabilities at the like basal hardware level up to maybe an algorithmic level where, maybe some algorithmic primitives, I like to call them, are like really easy on some kind of hardware and not so easy on another, and vice versa. And maybe there's a world, or maybe our world is like this, where we can sort of stitch together these different hardware systems and won't have a like single platform that wins the race, let's say.
Yeah. Well, Dominic, that's fascinating. I mean, I think it's really interesting how the question of simple verification of advantage opens the door to all these much, much deeper and broader. And I can tell you have a philosophy background because of the nature of the way you approach these questions. But I'm very, very impressed, and I'm excited to see where your research goes next. So thank you so much for joining me today.
Yeah, thank you so much, Sebastian. This has been a lot of fun.
Thanks again to Dominik Hangleiter for that conversation. I love the way he framed the quantum advantage question as a fundamentally epistemological one. When do you have enough circumstantial evidence to be convinced of something that you can't directly verify? The comparison to how we validate the Higgs boson discovery really stuck with me. If you want to go deeper, I strongly recommend Dominik's Quantum Frontiers blog series. It's remarkably accessible for the depth of the material, and his March 2026 paper on archive is a comprehensive read if you want the full argument. Links to both are in the show notes. If you want to go deeper on the topics that we cover, research highlights, commentary, and the occasional behind-the-scenes look at what's coming up for the show, sign up for the newsletter at newquantumera.com. It's free, and it's the best way to stay in the loop. And if you have an idea for a guest, a topic you'd like us to dig into, or just want to say hello, reach out through the website. I read everything. If you're enjoying the show, please subscribe wherever you listen to podcasts and leave a rating or review. It genuinely helps new listeners find us. If you know someone who's quantum curious, send them an episode. Word of mouth is still how most people discover the podcast. Thank you for listening. I'm Sebastian Hessinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.